Hello everyone, myself Dr. Aditi Chatterjee. Today I will discuss on the concept of poles and zeros. So first, we already know that from the definition of transfer function is basically Laplace transform of output by Laplace transform of input. So basically we are getting a differential equation of some order uh, in the numerator and the denominator. So here you can see here hs is the transfer function, and here the order of s in the numerator is m, and order of denominator mm, for s is n. Okay, so that implies we have m number of zeros as we have order of s as m, and here we will have n number of poles. From the numerator will be getting the zeros, and from denominator will be getting the poles. So this is a differential equation. In the numerator we are having a differential equation, in the denominator as well we are having a differential equation. Now if we factor this, we'll be getting factorized numerator and denominator, as which looks like s minus z1 into s minus z2 likewise. In the poles we are also having s. In the denominator we are also having factored terms as s minus p1, s minus p2. So from here, if we do ns, means this is numerator, ns equal to 0, we will be getting the roots. So that will give you the location of zeros. And if we make ds equal to 0, means the denominator, that will give you the roots which are called poles. So we are getting, means here also we can see that these are denoted by Z1, Z2. These are different poles in the system. And these P1, P2 are the poles of the system, which we are getting from the transfer function. So first we need to get the transfer function, which will be in S domain, and that will be a differential equation. One differential equation in the numerator and another in the denominator. By factorizing the polynomial equation in the numerator, the roots we will be getting, that will give you the zeros, and by factorization, the roots will be getting from the denominator will give you the poles of the system. Now, suppose let us consider a differential equation. So here you can see double derivative d2y dt2 plus 5 dy dt plus 6y equal to 2 du dt plus 1. So y is our output and u is the input. So the transfer function will be y by u. Ys in S domain by us. So what we have to do, we have to first Laplace transform this differential equation. If we have done double derivative d2y dt square, if we do Laplace transform, that will give you a square ys plus 5s ys plus 6ys. In the right hand side, it will be 2s us plus us plus 1. Sorry. So now ys by us is our transfer function. So the transfer function will be 2s plus 1 by s square plus 5s plus 6. So in the numerator, we have 2s plus 1. So if you equate this ns, or the numerator equal to 1, the root you will be getting, that will give you the location of 0. Now here in the denominator, the order of s, highest order of s is 2. So basically, in this system, we'll be having 1, 0 and 2 poles. And by factorizing this, you'll be getting the roots of s we will be getting 2 roots of s. So that will give you basically the 2 poles of the system. So in this transfer function, we have 1, 0 located at minus half, okay, and we'll be having 2 poles located, real poles located at minus 3 and minus 2. So for this differential equation, first we are getting the transfer function, and once you get the transfer function, we are finding the roots from the numerator, equating the numerator and denominator equal to 0. From equating that equal to 0, we are getting the roots of the transfer function, which gives us from the numerator we get zeros, and from the denominator the roots are basically the poles of the system. Similarly, another example where the poles are located in the complex conjugate of the S-plane. Now here also you can see that it is given, means the reverse thing we are doing. Previously, what we have done, we have the given differential equation. From there, we are finding the location of poles and zeros. Now in this example, the location of poles and zeros are given. The gain k is also given. Now you have to find the differential of equation of the system. So here we have 1, 0 located at minus 4, and we have 2 poles located at minus 1 plus minus 2j. So we can form this transfer function. In the numerator, we will be locating the 0, and the denominator will be comprises of the poles. So solving this, we are getting s plus 4 by s square plus 2s plus 5. So in the, if ys is the output and us is the input, so basically we have ys by us equal to this one. So if you simplify or cross multiply, you will be getting d2y dt square plus 2 dy dt plus 5y equal to 3 du dt plus 12 du. This is the differential equation of the system. So in the previous slide, we have seen that if the differential equation is given, how to find out the location of poles and zeros, and again, if the poles and zeros are given, then how to get the differential equation. Now in time domain response from pole zero plot, we can understand or we can comment on the stability of the system. From location of poles and zeros of the network function in the S-plane, the time response of the network can be perfectly identified. Means you will be able to comment on the stability of the and nature of the system, nature of the response. Poles mainly decide the nature of the response, while the zeros decide the magnitude of each part of the response. Now, suppose this is the first time domain response from pole zero plot, which we'll be discussing. So let us consider we have real and negative pole. Means the location of pole are basically or the roots are basically negative. Means it could be like -2, -3, -4, any real negative pole. So if we consider A, then the function will be given by Laplace, means transfer function will be given by 1 by s plus a. Okay, so here you can see 1 by s plus a. Now if you want to draw the time response, time domain analysis, then we have to take it to the time domain. Now fs is in Laplace domain, s domain. Now, if you want to take it to time domain, you have to do Laplace inverse. So, Laplace inverse of fs will be given for 1 by s plus a is given by e to the power minus 18. So, if you plot the response, we used to get this type of response. Okay. So, as time increases, it is getting saturated. Okay. So, if we have negative real poles, in the S plane, then the response we get are exponential response of e to the power minus at. So for poles which are real and negative, the time domain response looks like this. So it shows stable system. When the system response go towards infinity, it is considered as unstable system. So suppose if we have two negative pole located in the left hand plane. Suppose let us consider one located at -2, another located at -5. Then the response looks like this. This is for e to the power minus 5t, and this is e to the power minus 2t. So as A increases, means when we have more negative, the response means the decay is faster. Okay. Now if we have two repetitive negative real pole, means 1 by s plus a whole square. We have repetitive pole located at -a. Then the response is given, looks like this one. This also shows stable system. Now if we have repetitive pole located at the origin, then the time domain response looks like this. So you can see here, if the time increases, as t increases, the response is going towards infinity. So this type of network are basically unstable in nature. And so if we have two poles located at origin, the system response we can see is going towards infinity as t increases. So this type of response are basically unstable, and the system we get from this type of transfer function are unstable. So the transfer function is 1 by a square. Now, if we have real positive pole, means we have pole located at in the positive real axis. If we take Laplace transform, the transfer function is given by 1 by s minus a. Now, for time domain analysis, we have to find Laplace inverse. So, if we take Laplace inverse of fs, we will be getting ft, that is equal to e to the power plus at. If you draw the response, it looks like this. So this is also, as time increases, this is also going towards infinity. So obviously the system will be unstable. So from here we can see that if we have real poles located in the negative half or negative s plane, then the system response in the time domain is stable. But whereas if we have positive pole, positive real pole, then the system response gives us unstable system. The system response going towards infinity, which implies the system will be unstable. So if we have poles located in the left half of the S-plane, the system gives a stable system. But if we have poles located in the right half, then the system gives responses which shows instability. Now, if we have poles located on the imaginary axis, here we have two poles located in the plus j omega and minus j omega. So the response transfer function will be 1 by or some gain k by s plus j omega into s minus j omega. So if you simplify, then we'll be getting a by s square plus omega square. So this is in S domain. If you take Laplace inverse, then this will give ft will be equal to a sine omega t. Now, if you plot this, that time domain response looks like this. So with time, it will go on oscillating. So this is basically this type of response are known as sustained oscillation, and the stability is marginal stability. So if we have poles located in the j omega imaginary axis, then we get sustained oscillation as t increases. And the system, if we comment on the stability, it is basically marginally stable. So whenever we have nodes located on the imaginary imaginary axis, this type of systems are known as critically stable. Now, if we have poles located in complex, means complex pole with negative real part, means the poles will be in the negative half left hand plane, but complex. So here you can see the location of poles is minus a plus minus j omega. So here minus a is the real part and j omega is the imaginary part. So the system means the transfer function is basically k by s plus a whole square plus omega square. Now, if you take Laplace inverse, you will be getting for s plus a, it will give e to the power minus at, and the Laplace inverse of s plus a whole square plus omega square means basically s square plus omega square will give you sine omega t. So the time domain analysis, time domain representation of this system is basically e to the power minus at, some gain into e to the power minus at sine omega t. So basically, if you plot this, there will be envelope of e to the power minus at for sine omega t. So in between we'll be having sine omega t with the envelope of e to the power minus at. So if you follow this, this is not going towards infinity. So this is also give us a, or we can consider this as a stable system. So whenever we have complex pole with negative real part, this will give you a stable system. Now, if we have complex pole with positive real part means you can see here, if you equate this, you are getting A. So for S minus A, we have pole located at plus A plus minus j omega. Okay. So if you do Laplace inverse for this A phase, that will give you the time domain representation will be e to the power plus at sine omega t. So now the envelope on sine omega t will be for e to the power plus at. So the plot look like this. The time domain response sine omega t with the envelope of e to the power at. So you can note here that with increasing time, the plot is going towards the time domain response is going towards infinity. So this type of response is considered as uncontrollable, and the system is unstable in nature. So if we have repetitive poles in the imaginary axis, that will also give you unstable system. Okay, so if we have two poles, it means a square plus j omega square, a square plus omega square, that gives us critically stable system. But if we have a square plus omega square whole square, that will give you unstable network. This is the response for repeat double pole. We have two pole at plus j omega and two poles at minus j omega. So for repeated pair of poles on the imaginary axis, we get unstable system. If we have single pole at the origin, means 1 by s or k by s. So if you take Laplace inverse, that will give you k. So the response looks like this. This is basically step response. So from the above discussion, what we can conclude that a nature of the time response FT can be predicted from the pole zero plot of the network function. So each time you don't need to plot the time domain. From the location of poles and zeros, you can comment on the stability. What we have seen that if we have poles located in the left half plane, or if we have negative poles, it would be negative complex also, then we used to get stable system. But if we have poles located on the right half plane, means positive poles, and then we used to get unstable system from those transfer function. And if we have poles located on the imaginary axis j omega, then we get critically stable system because of sustained oscillation. From the discussion of the above cases, it can be concluded that location of poles in the left half of a plane, whether real or complex, are responsible for stable, controllable response, while poles located in the right half planes are responsible for unstable and uncontrollable response, indicating unstable network. Simple non-repetitive pair of complex pole on the imaginary axis produce pure oscillatory response. Repeated complex poles located purely on the imaginary axis represents growing oscillation, which implies unstable system. A single pole at the origin represents step type of response, while repetitive pole at the origin represent unstable network. The zeros decide the amplitude of the frequency domain response from pole zero. So that's all about pole zero plot and how you can comment on the stability from location of poles and zeros. Thank you. See you in the next lecture.